All right, so let's resume our discussion on the field theory. So, for this video, we assume that all fields that will appear are subfields of C. So, when a field is a subfield of C, so that necessarily contains Q because since it's a field, one is there. So, since one is there, Z is there. And again, since K is a field, so M by N kind of thing. So at M and N are integers, and non-zero also be inside K. So naturally that says Q has to be in K. So thus all subfields of C necessarily contain Q. So this is what is our standing assumption today is. Now we consider two fields K, subfields of C, K and L, such that K is further contained in L. Furthermore, we also assume that the degree of the extension is finite. So this is not, let me just remind you, this is nothing but the dimension of the vector space, L over K. So if degree of extension, so if the extension is a finite degree, then in the, recall that in the last video, we proved that for every alpha in L, there exists a unique, irreducible, monic polynomial f such with coefficients from K such that f of alpha is 0. So if for an extension, if this happens for an alpha, then we call alpha an algebraic element over K. So thus so we call it algebraic element if alpha satisfies. So we'll say alpha is an algebraic element. So yeah, so in this terminology, what we have just proved in the last video is every finite extension is algebraic. So in the sense that every element of the extended field is algebraic over the bottom field. Okay, so next I'll let since I don't remember whether I have mentioned that in the last video or not. However, let's even if at all I have done so, let's repeat it here because that is somewhat important for us. So in fact, I would like to leave this as an exercise. So suppose alpha belonging to a subfield of C is an algebraic integer. So then alpha, there is a minimum, there is a polynomial, monic polynomial with integer coefficients such which has alpha as a root, right? And since it's a monic polynomial with integer coefficients, it can be viewed as a polynomial with rational coefficients as well. So that means that you get a polynomial over Q which has alpha as a root. So that means alpha is an algebraic element over Q. So thus if alpha is an algebraic integer, it is an algebraic element, it automatically becomes an algebraic element over Q. Well, let's make a terminology that for an extension or for any complex number alpha, if alpha is algebraic over Q, then I will call alpha an algebraic number. So thus what we have seen is every algebraic integer is automatically an algebraic number. So now what I want to say about say here is about the minimal polynomial of alpha. So if alpha is an algebraic element integer, then the minimal polynomial alpha has coefficients from Z. Let me repeat what minimal polynomial is. So the minimal polynomial of an extension is by definition the unique monic irreducible polynomial whose existence whose existence we have already prove that if there is a polynomial over k that has alpha as a root, then there will be an irreducible polynomial over k which has also alpha as a root. So for any given alpha of an extension, the unique monic irreducible polynomial f for which this happens, we call this f as the minimal polynomial of alpha. So since in this exercise, since alpha is an algebraic integer, so it's an algebraic number, that is, it's algebraic over q. So we are allowed to talk about the minimal polynomial of alpha over q. So this exercise has asked you to prove that that minimal polynomial has all coefficients from z. So the reason for leaving it as an exercise, this is just a straightforward application of something called Gauss lemma. So which I presume that you must have seen in your ring theory course in MSc. So I hope that using the Gauss lemma, you can prove, you can do this exercise without any difficulty. Okay. So before we go ahead, let's recall one more thing, that there are two things. The first thing that I would like to recall, because I will use them again and again in this lecture, that considered in the scenario as above, that if alpha has f as the minimal polynomial, then we can consider the following map. Well, k alpha is defined as the smallest subfield of L that contains both k and alpha. So indeed, a priori, the definition of k alpha has a dependency on L. But you see, since at least in this discussion, we consider that all the fields that we will see are subfields of C. So if you don't like the dependence of k on L, you can simply say that it's a smallest subfield of C that contains both k and alpha, and actually that doesn't make any change. Okay, so our map is the evaluation map, that each polynomial, let's say g x, is being mapped to g alpha. Okay, then in the last lecture we showed that this becomes we get isomorphism. We get an isomorphism. And how does this isomorphism do? This isomorphism sends x bar, that is the coset of x, to alpha. That is the coset of x to alpha. And also we have one more thing, that from k to this field, there is an embedding which sends every small k of capital K to small k bar, as it is customary. So this you can immediately check as a ring homomorphism. So as it is customary to identify when two structures isomorphic, so what we will do it for each small k, we will identify that with k bar. So therefore, we in this way can assume that this field contains k, and this isomorphism. So after once this, after this identification, we can say that this idea, the isomorphism sends each every small k from here to small k itself. So thus it's an isomorphism of this to that, which fixes every element small k of capital K. Okay, this is one thing we have seen. And the second thing that we have also seen is the following, that suppose in an extension, alpha, beta, both are roots of some f, some polynomial over k, and assume that f is irreducible. And monic is not an issue, because you can always divide any polynomial by the leading coefficient. So thus what it says, that suppose alpha and beta are two elements in L which have the same monic polynomial, then in that case, in one hand we have this isomorphism we have this isomorphism from k alpha, okay, and then on the other hand we have the isomorphism k beta. So let's like earlier, we will assume that k is a subfield of this through this identification. So thus what we have seen is this isomorphism. In one hand, I have isomorphism from this to k alpha, and on the other hand, we have an isomorphism from this to k beta. So this isomorphism sends each k to k. So also this isomorphism also sends each k to k. Now it sends x bar to alpha, and this the left one sends x bar to beta. So composing them, we get an isomorphism from k alpha to k beta, which fixes every element small k of capital K and sends alpha to beta. Okay, so far so good. I hope that I discussed all what was necessary. And now let's get into one of our main theorem that we need today. So assume that, so as I said that today all the fields that we will see are over are subfields of C. So I assume that L over K is finite, and in fact let this be some natural number n. Then we are going to prove that K has, sorry, then we will prove that L has n number, exactly n number of embeddings in C. So what it means is there are n number of, well, of course I forgot something, fixing K, fixing each element of, so I'm saying that there are exactly n number of embeddings from K to C. Let's denote such an embedding by sigma, such that sigma of small k equals to small k for each small k in capital K. All right, so okay, so there are exactly m number of embeddings. So now let's try to prove that. So how to prove that? First of all, we choose an element from L, since it has finite degree, so L must be algebraic over K. So that means there will be a monic polynomial with coefficients from monic irreducible polynomial with coefficients from K, which has F as a root. So therefore we have this isomorphism that we have just discussed. All right, fine. Now if sigma is an embedding of suppose sigma is an embedding of L to C, then what we will do then, sigma of the image of so K is a subfield of L, so let denote sigma K is the image of K under the sort of embedding sigma, so which is also a subfield of C. Okay, so K and sigma K are by definition isomorphic. Then in the last lecture we have shown that whenever two fields have whenever there is an isomorphism between two fields, then the image of the irreducible polynomial image, in the sense that if we apply the embedding, the isomorphism on each coefficient of the polynomial, then the polynomial what we will get is also irreducible over this image field. And furthermore what we get is kx is isomorphic to sigma k. I think this is k, sigma kx by sigma fx. Okay. Now from here we have from here we have a let's say from here we have this isomorphism, and from here we also have another isomorphism to sigma k beta for any beta for any root of for any beta which is a root of the polynomial sigma f. So try to understand. From here we have this bijection, so we can perform this isomorphism. We can perform the same thing for the subfield sigma k with quotient by irreducible polynomial sigma f. Remember, sigma s is defined as applying coefficient, applying sigma coefficient wise. So for any beta of the sigma f, we have the isomorphism. So now if you just compose them, then what do you get? So what do you get? So you get an embedding of k alpha inside C, right? Because these are all subfields of C. You get an embedding of sub. Okay. I'm right, but I think I just stated the statement wrongly. So, okay. I'll just, I forgot I stated it wrongly, so I'll just correct it. It means every embedding sigma of k in C can be extended can be extended to L in n number of ways. So what it means is, if you take any embedding of k in C, then it admits n extensions, where n is the degree of the extension, n extensions to L. All right, so sorry for writing the statements wrong beforehand. So now let's concentrate here. So we have an embedding of k alpha. Indeed, we have an embedding of k alpha inside C, and this embedding sends, so here alpha goes to x bar, and here x bar goes to again x bar, because sigma of 1 is 1, and then here x bar goes to beta. So there is an embedding of alpha in C, which sends alpha to beta. Okay, fine. So by definition, L, so k alpha is the subfield of L that contains both k and alpha. So L alpha, this also can be extended, this also can be is also finite, right? In fact, this is less or equal to that of L and k. Okay, so L can be regarded as an extension of k over k alpha as well. And the equality means that k alpha, the equality means, from the formula that L over k is the product of L over k alpha and k alpha over k. So if equality happens here, then that means k alpha over k is one dimension, that is k alpha is just k. So k alpha is k, that only happens if alpha belongs to k. So what we do is, if I take any alpha from L which is outside k, if I start with an alpha, then this one has a smaller degree than this extension, Now we run an induction argument because we have now we have an extension of smaller degree. So any embedding of k alpha can be extended to an embedding of L in these many ways. So therefore every embedding of k alpha admits these number of extensions to L. Okay, and we have already seen that alpha and we have already seen that starting with any embedding of well, I made the mistake, it will be k. So starting with any embedding of k sigma, then when we pass through, so this we can do for any beta which is a root of sigma f of 0. So then how many roots are there? The number of roots is same as the degree of sigma f. So this is same as the degree of f, and the degree of f is certainly in the last lecture we have seen this is the degree of the extension. So what the upshot is the following, that for and we starting with an embedding sigma, we can get so we can extend the sigma, the embedding sigma of k inside C. We can extend that in these many number of ways. Okay, this is because any alpha should go to a root of sigma f, and root of sigma they are on the same as the number of the number of roots is same as the degree of the extension. So this therefore any sigma can be extended to an embedding of k alpha. So try to imagine first you have an embedding of k, then we extended that embedding to k alpha, and that can be done in exactly these many ways. And once I have extended that to k alpha, now we run an induction that allows me, that says that the embedding which has been extended to k alpha, that can further be extended to L in these many ways. So therefore so the sigma can be extended to k alpha in these in these many ways, and that can be further extended to L in these many ways. So therefore the sigma can be extended to L in these many ways, and that's exactly the product of these two is the degree of the extension. So that's what I have be starting with the sigma. I can extend that to L, the number of extensions. I can extend that to an embedding of L in these many number of ways. And now I just leave you to check. It's a straightforward verification that these are all extensions of sigma. Because it's very easy to see, I will just quickly say a line because I'm running short of time. So any sigma, so if we consider any extension of sigma, so once you consider that extension, on k alpha, then you see the image of alpha must be a root of this, and therefore it has already been counted in the list of extensions that we have already considered. So thus these are all extension of L, extension of any embedding sigma of k to L. All right, so now we will make a definition that says that an extension L over k, of course we consider finite extensions, is said to be normal if every embedding uh, of if every embedding of L into C, fixing K. What do you mean by fixing K is for each small k in capital K maps to small k. So if you consider any embedding of small k into C, any embedding of L into C, which fixes every element of small k, is actually an automorphism of L. We say the extension is normal if because so yeah, let's try to understand once again. So K is a subfield of C. So here so here the embedding is the standard one. So we knew that this embedding can be extended to an embedding of L into C in these many ways. Now normality says that all such embeddings will be actually automorphisms of L. Okay. So every embedding of L that fixes K must be an automorphism of L. Okay. Now we will tell you. I will tell you why this is relevant to our context. So this is the main point of our theorem. So before getting into the main point, so let me just recall a terminology. So suppose alpha has its minimal polynomial f, then all the roots of f are said to be conjugates of alpha. So I repeat, suppose I have an extension L over k and alpha is algebraic over k, then a conjugate of alpha is by definition a root of the minimal polynomial of alpha. Okay, so thus alpha has the number of conjugates of alpha is same as the degree of the minimal polynomial of alpha. Okay, so the theorem says K over L is normal if and only if for every L for every alpha belong to L, all conjugates of alpha will also belong to L. So what it means is, again, let me explain that alpha might be a root of the polynomial f. So here everything is over C, so alpha is a root of a polynomial f with coefficients from k. But when you see that coefficient, when you see that polynomial is a polynomial over C, so it can have other roots as well which do not belong to alpha. So therefore alpha might have conjugates outside L. So what it says that if the extension is normal, this doesn't happen, and that's a necessary and sufficient condition. So we will prove that. First of all, if so, proof of this direction that if for every element of L, all conjugates of that element also lie in L, then we will see that K is normal. That is in fact easy to see, because if you consider an embedding of L to C, so we will first show that an embedding sends a conjugate to another conjugate. So if embedding fixing K, that is for every small k in capital K, sigma of small k is small k. Then what happens that if let alpha be the let f be the monic polynomial, that x to the power n plus a n minus 1 x to the power n minus 1 plus a1 x plus a naught. So let this be the minimal polynomial of alpha, since by definition when you substitute alpha here, by definition when you substitute alpha here, then what you will get is this is 0. Now once you apply sigma to this, then what you get is sigma alpha whole to the power n, then sigma n, but sigma fixes each element of k, so therefore sigma of this is n minus 1, n minus 1, a1 sigma of alpha plus a naught is 0. That shows that sigma alpha, being a root of the same polynomial, is a conjugate of alpha. So thus every embedding of L into C sends every conjugate of every element of L to their conjugates, and since we have assumed this, that every conjugate of any element of L also lie in L, so therefore that shows that every the image of an element under sigma being a conjugate of that element also lie in L. So this direction is obvious. Now we will look at the reverse reverse direction. In the reverse direction, we will show that if k is normal, then all conjugates are inside. Okay. So what we do is suppose alpha and beta, they have the same minimal polynomial over same minimal polynomial f over k. Okay, so again, minimal by definition of minimal polynomial, it's an irreducible monic polynomial. So we know that now from what we have just discussed earlier. So we have an isomorphism from k alpha to k beta, which sends alpha to beta and sends each k to each k in k to k. Okay, so we have an embedding like this. Now what we do is so we will now consider L as an extension of k alpha. So now, so this embedding, so this isomorphism fixes k. So you can regard this embedding, regard this isomorphism as embedding on k alpha inside C, which sends alpha to beta and fixing every element of the bottom field k. Now we can extend these isomorphisms, this embedding, to many ways to an embedding. So in fact, the number of ways is same as the degree of this. So but we don't have to bother about that. We can, all that we need is this can be extended to an embedding of L to C. Because whenever we have an embedding, so we prove that for any extension, number of such extensions of an embedding is same as the degree of the extension. So thus this can be extended to an embedding of L into C. Since we have assumed that every embedding of L into C that fixes K, for every embedding of C that fixes K will be actually an isomorphism. So this embedding, since this extends an embedding that fixes K, so this embedding also fixes K. So therefore this has to be an isomorphism, hence its image has to lie in A. In particular, beta has to lie in L. Thus we assume that it's closed under conjugation, that if you take any alpha and consider all its conjugates, then it becomes normal. Okay, so we stop with just two things. As a corollary, we we can immediately achieve. And I want to leave you to an exercise that suppose so let alpha be a complex number. So let alpha be an algebraic number. So k alpha over q. So in fact, I think write instead of this q alpha. So alpha be an algebraic number. So q alpha is a finite degree extension of q. So this extension is normal if and only if q alpha contains all conjugates of alpha. This is because from the isomorphism from this map that we have just discussed earlier. From this map, since this is subjective, so image of this is same as image of that. So that means that shows that every element of k alpha is nothing but the image of some gx. So therefore, every element of k alpha is an polynomial alpha. So so if a typical element of this looks like following: a n alpha to the power n plus 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 a1 alpha plus a naught, then okay. So if then you apply a sigma on this thing that fixes q, what you get is a sigma alpha to the power n. Okay, so where sigma is an embedding of q alpha inside C fixing q. So since if you assume this extension is normal, then certainly since this belongs to q alpha, this also has to be in q alpha, right? So from that it will follow that all conjugates of alpha must be there. All conjugates of alpha must be there. So I leave the details to you. So as a consequence of this is the following, that suppose if you consider the polynomial z to the power n minus 1 equal to 0, you just take omega a root of that which is not equal to 1. Then q of omega over q is a normal extension. Is a normal extension because the roots of this polynomial are omega square, omega to the power n minus 1, and then of course 1. Okay, so here so this field not only contains omega, it contains all conjugates of omega, so therefore it is to be normal in view of the corollary. And then we just stop with introducing a notation that suppose I have an extension L over K notation. I have an extension L over K. It's a finite extension. As we said, I always consider finite. So G of L over K, we read it as Galois group of the extension. This stands for all isomorphisms of L, all automorphisms of L fixing sigma k equals to k for every k in k. You can check that it's a group with respect to composition. So given an extension, this Galois group is the group of all automorphisms that fixes the bottom field of the extension. Okay, I will stop here. As I said that since I assume that you must have seen some field extension, so this is just a quick review of the facts that we need further So there are many places where I have not provided all the details. Indeed, I have not provided all the details, and at some places I left something as I left things as exercises. So I encourage you to fill up all the details and solve the exercises that I've just suggested. So then, since this material, I presume that is already familiar to you, so therefore it should not be quite difficult for you. Rather, that is the way you will brush up your brush up your knowledge in field theory. All right, I will stop. So, as I said, if you have any queries, any doubts, or if you think that something that I have explained but you could not catch it, then please let me know. We can discuss. Then maybe, and we can discuss. And if you need, I can provide some more details. All right. So let's stop here.